Measuring delta E for chemical reactions. So a lot of chemical reactions either absorb energy from the surroundings or they release it to the surroundings. And that happens through heat and pressure volume work. So we now have equations for both of those. Heat is Q mc delta T. Work is negative P delta V. So those are the two processes by which it exchanges energy. Well, the change in internal energy during a chemical reaction measures all of the heat and work exchanged with the surroundings. So if we measure Q and W, then we can find out what the change in energy for that chemical reaction is. Well, if we set things up so that the volume doesn't change, that makes things simpler. W equals negative P delta V. If delta V equals 0, then W is 0, right? If W is 0, then delta E is just equal to Q. Things have gotten simpler. At constant volume, the change in internal energy for a chemical reaction is equal to the heat. We put a subscript V there to make sure everybody understands this is measuring heat at constant volume. If the volume changes, things get complicated. But we can set things up so the volume doesn't change. So this is called constant volume calorimetry. So calorimetry is a technique where we measure, that's where the meter part comes in, calories, we measure heat. It's not practical to measure the temperature of the chemical reaction. That's really tough. How do you've got two chemicals together, and how do you measure their temperatures, and then you've got a product coming in, it's not possible. So what we do is we let the chemical reaction do its thing, and we measure the amount of energy the heat that it exchanges with the surroundings, instead of trying to look at the individual chemicals. And we do this in something called a bomb calorimeter. And so in that calorimeter, we know that the Q for the system is equal to negative Q for the surroundings. That's what we've just been talking about. So if we make the surroundings the calorimeter, then Q for the surroundings equals Q for the calorimeter. We can measure Q for the calorimeter. We can measure its temperature change, its mass, its specific heat capacity. And then we can figure out Q for the system. So the reaction, the system, will either absorb or release heat. We're going to observe changes in the surroundings that let us figure out what's going on in the system, because we can't measure the system directly. This is a picture of a bomb calorimeter. This is the bomb part. It's an airtight chamber, and these are typically used for combustion reactions. If you want to know the amount of energy in a peanut, you can burn a peanut in here. There's oxygen in there, and you can measure the heat released by burning one peanut. The mass of the peanut, you can figure out some cool stuff. So there are ignition wires going in here because you get this whole thing set up, and then you need to start this on fire. And so you use the ignition wires to do that. There's oxygen in here. And then this little bomb is surrounded by a tank of water. And this is insulated so that the water is not going to exchange any energy with its surroundings. We've got a thermometer in here so we can measure the temperature of the water. We've got a stirring mechanism so that we can keep the water moving and have it all be at the same temperature. So we can measure the temperature change of the water. We know the mass of the water, the specific heat capacity of the water. From that, we can calculate Q for the reaction. With a calorimeter like this, instead of looking at the specific heat capacity and the mass of the calorimeter, we tend to use the heat capacity, which lumps those two things together, because the calorimeter itself is the same every time. And so then we just have this one unit here. So Q for the calorimeter equals the heat capacity for that calorimeter times the change in temperature. that's going to equal negative Q for the reaction. Q for the reaction at constant volume is equal to the change in internal energy for the chemical reaction. So we can do a problem like this. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees to 38.13 degrees Celsius. Find the change in energy for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. Again, with the lots and lots of numbers. Let's pull them out. 1.550 grams of hexane, C6H14. That's a mass. Let's call it M sub H, mass of hexane. And then we've got, we have an initial temperature that is 25.87 degrees Celsius. And we have a final temperature, which is 38.13 degrees Celsius. While we're thinking about it, we might as well just calculate the change in temperature, because that's what we need. Final minus initial, 38.13 minus 25.87, 12.26. That's the change in temperature for the calorimeter. I'm going to call that delta T cal. That's for the calorimeter. Find delta E, okay, and then there's one more number here. 5.73 kilojoules per degree Celsius. That's the heat capacity for the calorimeter. So what we know here, we're trying to find delta E for the reaction. That's going to equal Q at constant volume, which equals Q for the reaction. The reaction is giving off heat. The heat is going into the calorimeter. So this equals negative Q for the calorimeter. The heat lost by the reaction is gained by the calorimeter. We have this information about the calorimeter, the change in temperature and the heat capacity. So Q for the calorimeter is equal to the heat capacity of the calorimeter times the change in temperature of the calorimeter. So delta E for this reaction equals negative, C-cal is 5.73 joules per, kilojoules per degree Celsius. The change in temperature is 12.26. The degrees Celsius cancel out. So I've got negative 5.73 times 12.26. This gives me negative 70.249. I've got 3 sig figs because of the Q for the calorimeter, and the units are kilojoules. That's the amount of heat given off when 1.550 grams of liquid hexane burns. Any questions about that? They're asking us how many kilojoules per mole of hexane. Well, how many moles of hexane is that? Off the top of my head, I have no idea. Could we figure that out? Sure we could. So 1.550 grams of hexane. We need the molar mass. So that would be 6 times 12.01 plus 14 times 1.008, 86.172. So 1.550 divided by 86.172 equals 0.01798, 4 sig figs, 72 moles. This many kilojoules are released for this many moles. If I travel 120 miles in 2 hours, how many miles per hour is that? I take 120 miles, I divide by 2 hours, that's 60 miles per 1 hour, right? So to get kilojoules per mole, we're just going to divide by the number of moles that generated that amount of heat, 0.0179872 moles. So 70.249, it's a negative number, divided by 0.0179872 equals minus 3905.4 3 sig figs kilojoules per mole. How do we round that? Is that minus 391 kilojoules per mole? The original number is minus 3,905.4. We're supposed to round to the nearest 10. So the nearest 10, we would make this a 1. The nearest 10 is 3,910. Right? So we could say negative 3,910 kilojoules per mole. Or we could put this in scientific notation, minus 3.91 times 10 to the third kilojoules per mole. Just be careful when you round numbers like that. Any questions?